Welcome to MOOC's course Mechanical Unit Operations. The title of this particular lecture is Size Enlargement Methods. Till now we have seen the requirement necessity of the size reduction, how to do the analysis of the size reduction process, what types of size reduction forces are existing, what kind of equipment are available, those things we have seen. We have also seen the storage and conveying of the bulk solids, crushed solids and then lumps as well. Those things we have seen, but sometimes it is also necessary to do a kind of size enlargement for a few type of applications. So that is the reason this particular module we are going to discuss size enlargement methods and then equipment available for the size enlargement of fine particles. So before going into the details of the size enlargement methods, first let us discuss about why this size enlargement is required, under what conditions it is having a kind of important role. Is it necessary to do always kind of size reduction? What is the in general size of the particles that they should be enlarged, those kind of things we see, and then we see the effect of such particles if we don't do the enlargement. So why size enlargement required? Because fine particles, we understand that they are very difficult to handle, and in bulk they do not flow readily. That is what in general we have seen. Even the previous modules in the storage and conveying section also we have seen, if the particles are very fine, what happens, they may be, let us say it is a kind of bean or a kind of hopper is there. So then if the particles are very fine, they may be sticking to the wall, right, clinging to the walls in general, and they may not be falling down comfortably, right, when this valve is open at the bottom. Or sometimes they may be forming a kind of bridge just above the this discharge opening. They form a kind of bridge, such a kind of friction they have amongst themselves. So they have a kind of bridging, so that whatever the material is there below that bridge formation, that may be discharged, but above that one, that will not able to discharge, and then this bridging is having such kind of strength, so that will not allow the material to flow down. These kind of issues we have seen, and then these kind of issues are very much severe, especially for fine particles. Why it happens? Because they have the tendency to adhere together as conglomerates due to a result of action of their surface forces. They have surface forces. Surface forces come into the picture, especially when the particles goes towards the smaller and smaller size. Very fine particles, they have a kind of surface forces, like they may have the electrostatic charges, they may also have a kind of van der Waals forces, etc. Those kind of forces, they try to make these particles to come together and then form kind of a conglomerates. Those surface forces are playing a kind of active role, and then because of those surface forces, these fine particles, they tend to adhere together to form conglomerates. And then further finer the particles, the greater is the specific surface of the particle. So if the specific surface of the particle is large, or the particle is very fine, that means very small size diameter particle, then in general it will take a long time to settle down. Because of that one, what happens, this gravitational forces acting on that particle would be very small. Though the gravitational forces, whatever they make this particle to settle, so they may not be settled. Because of, let us say, this room, they may be having several fine particles, dust particles, very very small particles, which we may not able to see with naked eyes, but they are suspended. Still the gravity is acting, but the gravity is so small for those particles that they will not be able to settle down, or they settle down in infinite time, okay, very large time. So under such conditions, what happens, they stay apart from each other during the flow, so then they will not able to transport it easily. Then what is the remedy? The simplest remedy that one can use a kind of a glidant. The glidant is a kind of external material that is a kind of fine powder that forms a kind of a layer amongst the around these fine particles, and then that will reduce the surface forces. Like even those some of the glidants, they also avoid or reduce the electrostatic forces or the strength of electrostatic forces, so that they can flow freely if the separation or the flow strength is sufficient enough for the flow to occur. So what are these glidants? Glidants are very fine powders which are capable of reducing interparticle friction by forming surface layer on the particles. Okay. So let us say we have a kind of fine particle like this. like this. So then these glidants, they form a kind of layer around this surface of this particle, right. So that what happens, that whatever the interparticle friction is there between this particle, that will be reduced because of this interfering layer formed because of this glidants. So that is the purpose of using this glidant, so that this interparticle friction may be reduced by forming a layer along the surface of the particles, right. So that the friction arising from surface roughness may be reduced, and then accordingly the conglomerates, the particle adhering together, that particular phenomena may be reduced. Glidants can also reduce effects of electrostatic charges as well. So not only the surface forces, other surface forces, reducing interparticle friction, etc., they also reduce the electrostatic charges as well for such fine particles. But the problem is about this particle, they are much smaller than this finer particle themselves, and they are forming a kind of powder layer. They are kind of powder material and then forming a kind of layer. And these materials should have a kind of similar, if not exactly same as the ingredient material or active ingredient material. Let us say whatever the fine particles that we have, we are worried about their transport and handling. Let us say those particles, let us call active ingredients. Along those, when you take these glidants mix with the active ingredients, solid, that is finer particles, so then these glidants are maybe forming a kind of layer, but this glidant should have a similar thermophysical properties as a kind of active ingredients, right. And then they should be inert, they should not be reacting, or they should not be causing some kind of other kind of physical changes, if at all some temperature is also included in the process, those kind of thing. And then other important thing is that sometimes you need only active ingredients to be participating in the subsequent processes after the conveying. Let us say there is a reaction. So before the reaction, these fine particles are very difficult to flow. So then you mixed with the glidant, and then after using the glidant, you are comfortably able to move these particles to the unit process where the reaction is supposed to take place. But the reaction has to be taken place with a fluid, let us say surrounding fluid, heterogeneous reaction is taking place. That reaction has to be taken place with a active ingredient only, not with the glidant. So in such case, before the reaction, you need to separate out those glidants. That is the another additional problem arising with this glidant. One more issue is that you may not find a kind of suitable glidant for all kind of materials. For some kind of material, you may find a kind of suitable glidant, but finding such kind of glidant for all other kind of materials is a kind of very difficult task. So that is the reason, rather trying to find out the glidant, it is better to optimize the size of the particles, usable level, like workable size particles. You try to make or have a particle sizes of such a kind of large size which can be workable, which can be easily transportable, and then which can be easily reactable or undergo some kind of momentum or heat transfer, whatever the, if there is a reaction, whatever the process are there. So that should comfortably take place. That is what the purpose. So it is better to have the particles of such kind of size, right. Because of this reason, if you can enlarge the fine particles, then they may come to the such a kind of certain bigger size, and then those size particles may be comfortably undergo subsequent operations, right. And then this size enlargement should be very controlled. You cannot have a kind of from very fine particles of some microns or some nano size to the almost like when you do the enlargement, you may be getting to 1 centimeter, 2 centimeter particles, such kind of big lumps you are forming. That should not be the case again. It should be controlled process. Okay. So that is the reason optimization of particle size is far most important method of improving the flow properties of solids rather than using the glidants, because of the reasons that I mentioned. Now, we have also seen that fine particles may be difficult to discharge from hoppers, because sometimes they may be clinging to the wall surface of the container, and then they may be forming a kind of bridges, as I already drawn a picture and shown in a hopper, something like this. You may be having fine particles filled over here, so entirely. So then what happens, the fine particles may be sticking to the walls. You may not be able to discharge them properly, right, like this. right. So, like these particles may be sticking to the wall sometimes, and then sometimes what happens, a kind of rat hole formation kind of thing will be there. So, that is the material above the discharge rat hole that may be discharging, but the other material may not be discharging because there is a kind of interparticle friction, and then that keeps those particles together like this. So, they are not flowing, right. So, only that material whatever in the rat hole, that is only going comfortably. Sometimes we have also seen that the kind of bridge formation takes place like this bridge formation of the particles will take place. So, what happens, the material whatever the material solid fine particles below the bridge formation level is there, that will be taken down, that may come comfortably, but the material which is above the bridge, that may not able to flow down, because the particles interparticle friction is so high that the particles are coming othering together and then forming a kind of bridges, and then they are not allowing the material above them whatever is there that to flow down. So, these kind of issues are there, so that we have already seen. So, as particles may cling to the walls, particles may form bridges at the point of discharge. So, although these kind of problems we have already seen that if you provide mechanical vibrations or shaking, mechanical steering, or vibrations etc. along the walls of this container or the silo or the hopper, so then it is possible that you may reduce such kind of effects of bridge formation, or you can reduce the influence of the rat hole formation. You may even reduce the particles sticking to the wall, clinging to the wall, those kind of things also you can reduce, but you cannot completely avoid such kind of phenomena by using mechanical vibrations or mechanical steering kind of thing, right. So, because of that one, it is always possible to have a kind of a solution, maybe to increase the particle size by forming them into aggregates. That is the kind of best solution, best possible, if not the best, satisfactory solution. That is going to be a kind of satisfactory solution where you can conveniently move, or the allow where you conveniently make solid particles to move conveniently or flow conveniently. That you can make sure with a kind of satisfactory kind of things. If not by if it is not a best option, it is a kind of satisfactory option. So, increasing the particle size by size enlargement methods is a kind of going to be very useful. However, the problems associated with the fine particles we have seen till now are only associated with their flowability kind of issues only, but in general they may also cause some kind of health issues as well, that we see now. Fine particles may also give rise to serious environment and health problems. What happens, let us say, when you are loading or unloading a vehicles which is having like these fine particles, let us say fine particles you are loading in a vehicle, or already fine particles are loaded in a container and then you are taking out, unloading it. Then during that process what happens, this fine particles may form a kind of a dust cloud in the surrounding, right. So, that is very dangerous. And then surrounding weather, if it is in a kind of windy condition, weather is windy weather, then this dust cloud may be carried to the long distance, and then that may be causing health problems to the not only the people working in the industry in the process, but also nearby surrounding society as well, that is going to affect, right. So, that is the problem. So, in such cases what happens, even if these fine particles are inert, right. So, when you inhale them, even if it is inert, that is going to sting onto the lungs, and then that may be causing some kind of respiratory problems. That is a kind of major issue. Now, when they are non-reacting, when they are inert, and then when you are inhaling them by because the weather is surrounding air is contaminated like that, then they are sticking to the lungs, and then creating a respiratory problem. Now, you can imagine if these particles are reactive also, if they may also cause some kind of physical or chemical changes inside the body, then you cannot even imagine what kind of health issues arise. So, such is the kind of dangerous problem about these fine particles, especially concerned with the environment and health problems. So, as they may form dust clouds when loaded into the vehicles, may become dispersed over long distance in windy conditions. Even if fine particles are inert, serious respiratory problems can result if they are inhaled. It may be noted that particular health hazard imposed by asbestos is largely associated with the size and shape of the particles and their tendency to collect in the lungs. Because of these reasons, these asbestos particles in general which are inhaled, because of this such kind of environment in the working place, they are causing respiratory problem because of their size and shape and then their tendency to collect in the lungs. So, this is other kind of problem of handling very fine particles. So, size of the particles may be increased from molecular dimensions by growing them by crystallization from both solution and mels. What you can do, you can find out a kind of a solvent in which these particles may be dissolved. So, then you dissolve them and then you recrystallize them. So, that this final particle initially you dissolve, but when you do the recrystallization you may not be getting such fine particles, you may be getting such a you may be getting a slightly bigger particles. Okay. So, dissolving and recrystallizing may provide a mechanism for controlling both particle size and shape as well. So, fine particles may also be condensed out from both vapors and gases before letting out the industrial effluents, let us say industrial effluents, gases or vapors, whatever having particles or particle laden vapors or gases, rather just releasing them from the industries. Before releasing them, one can condense them and then collect a kind of bigger particles, and then only cleaner gases or vapors should be released out. Desired particle size may also be achieved by building up from fine particles, such as production of fertilizer granules by agglomeration or by a repeated coating process. Fertilizers in general, we do a kind of agglomeration. The fertilizers also, they need a kind of specified size. You cannot have a very fine particles, very small size of the fertilizers, because they are in general used in kind of farming, etc. So, in the field, when somebody is spraying these fertilizers, if they are very small and then catching up in the surrounding air, so that is going to be dangerous to the people working around. So, that way also the fertilizers need to be of a specialized sizes. Okay, they cannot be very fine, very small, very fine sizes. Then formation of pellets or pails of medical purposes by compression of particulate mass. So, sometimes especially in pharmaceutical industries, we see tableting, etc. Tablets consist of several particles. So, one cannot take those particles as it is. So, then a kind of briquetting or tableting is done by the compressive forces, compressive action. That is one of the size enlargement method that we are going to see anyway. So, here we can have a kind of binding agent along with these particles. So, that binding agent will give a strength to the material, and then the tablet one can have, right. So, this will also add a kind of addition, like tableting, a certain exact how many grams of the material should be present in the given, or how many grams or milligrams of the active ingredient should be present in a given tablet. Those kind of thing, controlling and metering can also be done by a exact pelleting or briquetting of these tablets. So, then what is size enlargement? So, we have seen already several reasons why size enlargement should be done. There may be many other reasons also, right. So, we have now enough number of reasons to study why size enlargement is required, right. So, first let us see what is size enlargement. It is any process whereby small particles are agglomerated or otherwise brought together into larger, relatively permanent masses in which original particles can still be distinguished. Okay. So, that is what, when you do this, you take few particles and then you do a kind of agglomeration process, so that you can have a kind of bigger particles, right. Bigger size particles you can have, comprising of such small particles, but they should not be very loose, that when you give a kind of small forces, these particles may be these enlarged particles may be disintegrating immediately, right. But they should not be very strong, that if you wanted to disintegrate them, then you need to give a kind of additional forces, extra forces kind of thing. Okay. They should be relatively permanent masses. Let us say you have taken tablets. So, the particles are a kind of active ingredients, but you are adding some kind of binding agent, so that you can easily make a kind of a tablet which is having sufficient mechanical strength. But if the mechanical strength is so high that even when you inhale it, it takes several hours to dissolve inside your stomach so that the active ingredient should come out and then be active and then show its effect on a kind of a disease. So it is not going to work. It should be dissolved, it should be disintegrated as early as possible. So those kind of things should be taken care. So that is the reason size enlargement is any process whereby small particles are agglomerated or otherwise brought together into larger relatively permanent masses in which original particles can still be distinguished. Okay, so they should not be very loose also. If they are very loose, by from the point of production to the consumer point by the reaches, all the particles, the enlarged particles may be disintegrated and then smaller particles may be forming. So that is not going to lose either way. It should be controlled properly. So where do we find such kind of size enlargement in general? We find in pharmaceutical and food processing industries. We find in consumer products, specified size and shape of the products are required. So that is what we call consumer products. And in fertilizers and detergent productions, detergents also need to be in a kind of specified sizes. They cannot be very fine. Otherwise, they may cause a kind of environmental and health hazardous to the people using them. Then mineral processing industries, etc., where we use in general the size enlargement methods. So agglomeration is the formation of aggregates through the sticking together of feed and or recycled material. So whatever the material, that feed material is there, you sticking together and then form a kind of certain bigger particles. That is what agglomeration. So now what should be the objectives of size enlargement in general, right? So let us say in agricultural chemical granules or pharmaceutical tablets, the objective should be they should provide provision of a defined quantity to facilitate dispensing and metering. So in a given size of the tablet, the amount of the active ingredients and an amount of the binding material, binding agent will be very much defined and then properly controlled. So that provision you will be able to have if you are doing this size enlargement and then tableting kind of thing, or you should do the size tableting kind of process such a way that in a given tablet you should have that much milligrams of active ingredients only. You cannot afford to have a variation or change in active ingredients composition from one tablet to other tablet. So that kind of provision of a defined quantity to facilitate dispensing and metering of these tablets, etc. Then improved flowability also. So when they are after forming by some briquetting operation or compressive kind of size enlargement methods, whatever the tablet that you bring, you will not be packing immediately in the wrappers. So you may be flowing from one process to the product collection vessel. So the flowability should be comfortable, and then during the flow process they should not break, etc., those kind of things. So that is improved flowability should be there. And then creation of non-segregating blends of powder ingredients, briquetting of waste fines such as elimination of dust handling hazards or losses, etc. Then granulation of fertilizers to reduce caking and lump formation. In general, in fertilizers, what happens if the particles are very small? So actually the process, you will be doing some kind of drying process also. So if the process is not done properly, a kind of caking or lump formation kind of thing will also be take place in general. So when you do the granulation of these fertilizers, one should be careful that they are not forming cakes or lump kind of thing, or that by size enlargement such a kind of existing caking lump formation should be reduced. And then increased bulk density for storage and tableting of the feeds, etc. Then control of solubility in instant food products and so on. So like that, if you application wise, if you see, their objectives also keep on changing and then slightly modifying from one to the other case, right? So these are the objectives with reference to some kind of specific applications of the size enlargement. Then agglomeration methods. So what we understand, agglomeration is kind of sticking together smaller particles, fine particles, and then trying to form a kind of bigger particle, right? So now how does it happen? What kind of methods are available? That is what we are going to see. Primarily there are two methods only, but we can have a kind of third method also. So we see these three methods. Like first one is the granulation or agitative agglomeration. Right, here agglomeration by agitation is referred to as a kind of granulation. Here what we have, you have a kind of a cylindrical vessel where or a drum kind of thing you are having. So in which you take the feed, includes like active ingredient, solid fine particles along with the blend particles, etc. So those drums rotate once you take this material inside, and then the agglomeration or the bigger size particle formation takes place. Right, this process can be continuous or batch wise as well. So here what happens, the mechanism primarily is the agitation. So whatever the agglomeration is occurring by agitation is referred to as a kind of a granulation process. Then sintering. Agglomeration may also be induced by heat, which either leads to controlled sintering of the particles bed or induce sintering or partial melting of a binder component of feed. Binder components of a feed in general a kind of polymer solutions or some kind of taste inducing agents or something like that. Okay. That is what the sintering process. This third one is the compaction or compressive agglomeration. Here what happens, the processes where the mixture of particulate matter is fed to a compressive device which promotes agglomeration due to pressure. This is in general used for a kind of a briquetting or tableting kind of thing, where you take the fine particles and then you apply compressive forces so that they form a kind of tablets. Right. So either continuous sheets or strands of solid material are produced, or some solid form such as briquette or tablets. So these are the three agglomeration methods in generally one can take. Primarily actually two only, granulation, the other one is the compaction, but sometimes sintering is also been used for agglomeration. Okay. Then stages in agglomeration rate processes. What stages in general you have? In general there are 4 stages are possible. 4 stages can be identified if the agglomerates are forming from a mixture of particles of uniform sizes, that is uniform mixture that you have. So from that uniform mixture of fine particles, if you take and then do a kind of agglomeration, so you may find the agglomerates in 4 stages. What are those stages? We see now. First one is the nucleation, in which fresh particles are formed by attrition. Next is the layering or coating. As material is deposited on the surfaces of the nuclei, the increasing both the size and total mass of the particles takes place. Okay, a kind of layering or coating of the fine particle will be done by this layering or coating mechanism or this step. Then is the coalescence. Coalescence of particles which result in an increase in particle size, but not in the total mass of particles. Whatever these small size particles are there, they come together and then coalesce and then they form a kind of bigger size particle, right. But the size changes, the size increases, but the total mass of the particle does not change. Whatever the, let us say you take 2 particles only, whatever the weights of individual 2 particles are there, if you add together, that should be the weight of the agglomerated bigger particle forming by the coalescence. Okay. Sometimes that entire 2 particles complete material may not be forming a kind of a bigger material. So one bigger particle and then some fractures may also forming. So that entire mass will remain same, though the bigger size particles are forming. Then attrition, this results in degradation and formation of small particles, thus generating nuclei that re-enter the cycle again. So those are the different stages that one may come across in kind of agglomeration. So granulation stages, so we have seen till now stages in agglomeration, now we see stages in granulation. So here we see this kind of pictorially. Here in a traditional description what we have a small nuclei, small kind of particles. So they join together because of the nucleation and then they form a kind of particle like this. Let us say that particle is like this and then you have a kind of a binding agent or something like that, the small particles here, right. So these particles will form a kind of a layer along the surface like this, or a kind of coating will take place. So this is known as the coating or layering or snowballing or onion skinning kind of names are given. So then you have a particle, bigger particle like this. Then coalescence is also one of the stages. So here let us say this one small particle, this one slightly bigger particle, they join together and then they form a kind of a bigger particle like this. They even come closer and then form a kind of a bigger particle like this as well. Then there is also kind of aberration transfer. So, let us say here now you take two same size particles. So, then in this aberration transfer what happens, some of the material goes in and transfer to the other particle. So, then one of this particle becomes slightly bigger. So, this particle is now slightly bigger compared to this particle, right, because some of this material is transferred into this material by the aberration, right. So, the obviously the remaining material, the remaining other particle, that size should be decreased. So, now you can see this shaded particle, this particle, its size is decreased compared to its previous size before the aberration transfer. So, this is what the aberration transfer. Then crushing and layers happening together. Here the particle is there, and this particle may be undergoing a kind of crushing by the attrition or something kind of those kind of processes, and then this will form a kind of a, after crushing, these smaller particles are forming a kind of layer along this the other particle, so that the altogether bigger particle formation takes place because of this enlargement, right. So, these are the steps in general considered in traditional granulation process, but nowadays in modern processes it is done slightly different way also. Whatever the small particles nuclei kind of thing fractures are there. So, here wetting and nucleation takes place. So, then some kind of solvent you can take, or slurry you can take, or some kind of, let us say, binding agent you can say. So, that when you mix here, so they are forming like this, and then further these particles may join together with the help of the additional fluid medium that you have taken, and they may be forming a kind of slightly bigger particle like this, though there may be some smaller particles still remaining, right. So, such kind of bigger particles, then they can consolidate and then coalesce, they can undergo kind of coalesce, and then they can form a kind of a bigger particle shown like this. Or this particle, whatever this after wetting and nucleation, or even after consolidation, these particles may also undergo some kind of attrition, because this process definitely the interaction between the particles will be there. So, then there will be a kind of attrition amongst those particles. So, then because of that one, some fraction of this material may be disintegrated, and then some small particles are forming. If the attrition is more, so then many smaller particles may be forming like this. So, that is what attrition and breakage. So, these are the granulation stages in general, both traditional approach and then modern approach. Next is the granule growth and then breakage mechanisms in granulation, that also we see. This is a kind of mechanism which has been taken from a reference book, where it was shown as a kind of steps for their optimization problem. This is not truly from kind of experimental work, but optimization problem, this is what we have taken, right. Okay. So, growth and breakage mechanisms in granulation. Here granule growth, how it takes place, if you have the smaller nuclei something like this, and then you allow this nucleation process to take place. So, let us say the particle you may be forming like this. Now, such kind of bigger granules that you have, so you may be having different size of granules. Let us say you have the smaller granule and then bigger granule. So, then they may coalesce, and then they may form a kind of further a bigger granule, and they are not necessarily kind of spherical, and they have been taken in a spherical shape just for a kind of reference, so that we can see, understand easily here. Okay. So, there is another process, layering. So, let us say one granule is there, smaller size granule that you form, but there are other nuclei available. So, they may be forming as a kind of layer along this surface of this smaller granule, and then you can have a kind of layered granules which is having size slightly bigger than the its initial size. So, this can also be layering, is also a kind of a granule growth stage mechanism, one of the mechanism. Now, granule breakage mechanism, how does it take place? Let us say you have already granulated bigger size particle, you shatter it, then you form a kind of nuclei like this. It is just a kind of reverse of the nucleation process. Then fragmentation, let us say you have a kind of bigger size granule. When you do the fragmentation, you can have a kind of two different sized granules, different shape and different size granules you may get because of the fragmentation. and there may also be a kind of wearing. So, when you do this wearing, the shape may be remaining same, but the size reduction takes place because of this one, and then so here smaller granule will take form, and then along with this there will be some kind of nuclei will also form. In the abrasion transfer we have already seen, so one bigger granule and one smaller granule is there. So, either of these two process may take place. This smaller granule, some of the material of this smaller granule may transfer to the bigger granule or attach to the bigger granule, and then kind of a bigger further bigger granule may be forming because of the abrasion, or otherwise the some of the material from the bigger granule may be coming and attaching to the smaller granule because of the abrasion, and then there may be a kind of intermediate size particle may be forming like this. So, here that is what other thing, like these fines, the dotted ones whatever shown in this picture are nuclei kind of, they are very fine small particles, they are very difficult to handle. So, they are not workable size, they are not in workable size. So, then workable sizes are in general like bigger, like circles etc. are shown here. So, they are working units kind of thing. Such kind of enlarged particles are better to handle and then transport. This is about the growth and breakage mechanisms in granulation. Now, we see some details about the agitative granulation or agglomeration, and then compressive agglomeration, and then those some details we see now here. So, agitative granulation, in general we have a kind of a vessel, in general a kind of drum, it may be having disc and then mixer and all those things. So, here let us say you have a feed, this feed is a kind of small size particles, very small size particles, but uniform mixture, something like this, right, very fine particles. These fine particles along with some kind of binding agents or kind of a size enlargement medium, they will be taken in a kind of process vessel, or after taking into the process vessel you can spray some kind of solvents or slurries onto this bed of particles, and then rotate this drum, so that to agitation may take place, and then because of that one, because of that agitation these particles stick together because of the sprayed slurry or solvent we have, whichever we have taken. Because of that one they will attach together themselves, and then they form a kind of bigger particles, something like this, right. So, which are in a kind of better workable size rather than here this such feed. If you see the size of each particle is very small. It is not one feed is not one single particle shown here. It is a kind of having so many fine particles as dotted particles like this here, right. When you do the agglomeration, they are all forming kind of lumps kind of thing, agglomerates kind of thing here, right, because of the agitation they have formed, and then this particle is a kind of in a better size to handle in subsequent in a given transport operation. Okay. So, here process variables for the feed, let us say x, and then for y it is a product, let us say y, right. This vessel E is a kind of some kind of process stages that are going down inside this equipment. So, it is a kind of generalized picture only. Okay. Here what happens in general, feed is introduced into a vessel along with granulating medium and agitated to get granulated product, and this process include fluid bed, pan or disc, drum, and then mixer granulators. This also used as a coating operation for controlled release, taste making, etc. Then feed typically consists of mixture of solid ingredients, that is fine particles or the active ingredients that I have been telling, those fine particles, then some kind of binders, they are something like polymer solutions or some kind of solvents or some kind of slurries, etc. Diluents may also be there, disintegrants may be there, flow aids may be there, surfactants may be there, wetting agents may be there, lubricants, fillers or end use aids such as colors, taste modifiers, etc. may also be there. It is not necessary that all of them may be there in each and every process. It is not that, it is not true. Depending on the applications, some of them may be there, some of may not be there. Depending on case to case, you may need some of them, or sometimes you may need all of them. But it is not true that always you need all of them. So, in such processes agglomeration can be induced by several ways. One way is a solvent or slurry can be atomized onto the bed of particles that coats either the particles or granule surfaces promoting agglomeration, or spray drops can form small nuclei in the case of powder feed that can be subsequently agglomerate, or alternatively solvent may induce dissolution and recrystallization in case of soluble particles. If the particles are soluble in a solvent which we have taken, then the particle may be dissolved, so that a kind of solutions or slurry it may be forming. That solution or slurry, if you recrystallize it, then you may be having a kind of a bigger size particle rather having a kind of fine particles as initially that you had. Okay. So, dissolution and recrystallization may also be one kind of a way that is causing this size enlargement. Any of these methods may be possible to have this size enlargement. Slurries often contain the same particulate matter as the dry feed, and granules may be formed either completely or partially as the droplets solidify in flight prior to reaching particle bed. Now, this is about the agitative granulation. Now, we see compressive granulation, how to do that one. Compressive granulation in general, what we have a kind of a setup like this. So, this, let us say 2 plates are there here, not kind of plates, sections are there like this, Okay. So, the fine particle, whatever the feed fine particle, very small size particles are there, they themselves as individual without any addition may come here, may be taken inside this compressive device, right, and then you apply compressive forces so that they may come together and then form a product like a tablet of this shape, whatever the shapes that we have, these kind of shapes tablets we may get in general. Right. So, sometimes it is not possible if you take only the feed material and do the compressive action, if you apply it may not be possible that you may get the required product size. So, then under such conditions the feed may be added with some kind of binder material or taste modifiers etc., as per the requirements, and then they pass through this thing. So, when they are passing through this one, these two sections may come close together because of the compressive forces, or when the compressive forces applied, and then the enlarged particle which are now product, they may be coming as a kind of product. Now, here you can say here also the initially very fine particles are there, after that you have a kind of particle slightly bigger size which are in a kind of workable size. They can be easily transported, they can be easily undergo a reactive process, whatever it is there. They can easily be disintegrated as well by dissolving or by applying some small strength without applying high strength. You can apply very less strength and then you can get disintegrating these products either way. Okay. So, that is they are large masses, but relatively permanent masses. They are not permanent masses. That means you can disintegrate them as well. So, this is about the compressive granulation. Okay. So, now typical agglomeration circuit. If you take any agglomeration section or circuit, there may be several operations involved, and then sooner when we see the schematic, we can understand that whatever the agitative granulation is there or agitative agglomeration is there, that is a kind of intermediate rather than a kind of final product, whereas the product that you get from the compressive units, that is a kind of a final product. So, that is what we see now here. Let us say typical agglomeration circuit looks like this, not necessarily that this is how each and every agglomeration unit will be there. There may be additions, there may not be these many units involved in these many unit operations may not be involved in a given agglomeration circuit, or in some other agglomeration unit much more number of unit operations may be involved than shown here. So, anything is possible, but this is just a kind of a typical agglomeration circuit. So, here what we have, we take these feed powders along with the ingredients from the ingredient bins in a blender like this here. So, this is rotates, this blender is having kind of agitative provision. So, when it rotates, the agitations will take place. So, from here you take that material to premix bin and then again add the binding fluid here, and then you do a kind of mixing so that granulation takes place, right. So, that a kind of granulation takes place. So, after here whatever the material, the granulated material is there, that you pass through classifier, or you pass through a kind of screens, so that you can separate the undersize oversized material, whatever the product, that oversized material. Now, here the oversized material should be a kind of product in general, because we are doing a kind of a size enlargement. They may be taken to the other granule bin. From there we may be taking them to a kind of a compressive device, where tableting may be done by the pressing operation, compressive operation, and then final products may be coming as a kind of tablets or briquetting. Whereas the undersized material, or the material which are small enough and which may not good enough to undergo kind of briquetting or tableting kind of operation, they may be taken to the recycle bin. From the recycle bin they may be taken again to the mills. They may be disintegrated by using the smaller strength mills, and then they may be taken back to the kind of a recycling unit, where the circuit continues, right. So, this is a kind of typical agglomeration circuit, where here now what we are seeing, that this is a kind of a agitative granulation step here, from here to here, right. So, here whatever the product is coming, that we are not taking as a kind of final product. After this we are doing a kind of classification, or using the classifier in the sense we are doing the size separation. So, size separation we do, and then the particles which are of suitable size, they may be taken to the kind of compressive device, where the compressive agglomeration takes place in order to get the product in a kind of tablet form. Whatever the material after the classifier which is not found good enough for the compressive action, they are further taken to the recycle bin. From the recycle bin they can be taken in a kind of small strength mills, where these particles, because after granulation they may not be suitable here, that is the reason they brought to the recycle bin, but they are enlarged. So, those enlarged particles will again disintegrated using these mills, and they will be fed back to the feed powder tanks, and then that process continues until the entire material has been converted as per the required size. So, what are the growth mechanisms? Two essential processes that can cause agglomeration of particles when they are suspended in a fluid rather than a kind of individual solid phase. When you suspend these fine particles in a fluid, then two essential processes may take place. They are nothing but perikinetic processes and then orthokinetic processes, right. So, we see individually perikinetic processes, these are attributable to the Brownian moment, that is even when you have a kind of stationary fluid without any bulk motion. So, at the molecular level, the molecular vibrations, interactions, molecular rotations, etc., those kind of things will be there. So, those kind of vibrations, rotations of the molecules induce some kind of motion, that is known as a kind of Brownian moment or the Brownian motion. So, these are whatever these perikinetic processes are there, they are attributable to Brownian moment. So, they may be existing even if there is no bulk flow, though these particles are suspended in a fluid, but the fluid is in a kind of stationary position stage. So, then under such conditions also these perikinetic processes will occur, because they are attributable to the Brownian moment. So, they can occur even in a static fluid. Further, double layer repulsive forces and van der Waals attractive forces may both operate independently in dispersed systems. Repulsive forces decrease exponentially with distance across the ionic double layers. Attractive forces decrease at large distance from the particle surfaces and are inversely proportional to distance. Fine particles may also be held together by electrostatic forces. So, now coming to these forces, attractive and repulsive forces, let us say we have a kind of y-axis which indicate the interaction forces between these particles, and then we have a kind of x-axis that indicates a kind of a distance between the particles r. So, these forces repulsive forces are acting like this, something like this, right. So, these forces decreases, and then decreases may not be a kind of it is a kind of this repulsive forces kind of exponentially decreasing with distance like this. then let us draw the figure first. So, these are the repulsive forces, they are decreasing, and then at this point what happens, the interaction force becomes 0, there is no interaction between the particles, and after that when you further increase the distance between these particles, then a kind of attractive forces increases up to this point, certain r value, and then further if you take these particles away from each other, so what happens, this attraction force started decreasing, and then there will not be any kind of attraction forces after certain distance. This distance is between these two particles, and then this itself, the particles are in a kind of micron size, and then this distance, this r is also in small dimensions, in some micron size, right. So, this is how these interaction forces in general may be there. So, under these conditions where these kind of forces are existing, so all those cases, under those circumstances, we have these perikinetic processes are having a role, whereas the orthokinetic processes which are occur where the perikinetic process is supplemented by the action of eddy current, which may be set up in stirred vessel or in a flowing system. The fine particles along with the fluid you may be taking in a kind of a vessel and then stirring them rigorously, or you taking or the flow is a kind of very high flow, so that eddy currents may be forming, something similar to the kind of turbulence, etc. So, under such kind of eddy currents presence, the influence of the Brownian moment may be very small, or in comparison to this eddy currents which are occurring because of the rigorous stirring or the high velocity flow system. So, in comparison to them, the Brownian moment may be very small. So, when orthokinetic process is dominating, the contribution from the perikinetic process may be very small. Both of them may be there, but the contribution may be very small. Let us say if the fluid is almost like a stationary, or if it is moving with very slow velocity, very small velocity, something like order of 10 power minus 6 meter per second or 10 power minus 10 meter per second, such small velocity, then there is a bulk flow, though it is a very small, but the bulk flow is very small. Under such conditions, Brownian moment or the process which is occurring because of the Brownian moment, that is more important or having the lead role compared to the bulk motion. Right. So, that is what happens in the perikinetic process. Orthokinetic process, it is different way. Bulk motion is so strong that the Brownian moment or the contribution from the Brownian moment can be negligible or considerably very small compared to the orthokinetic processes. In such circumstances where the stirring of the vessel having these contents of solid and fluid, stirring them, or the system is in rigorous flow, under such conditions the effects of the perikinetic mechanisms are generally negligible and orthokinetic processes dominate. For perikinetic processes, this size of the particle, let us say after time t, if you wanted to increase it to t size, dt size, so then dt cube is equals to a1 plus b1 t, that is suitable equation to represent this perikinetic process in general. For orthokinetic processes, you can represent the equation like in equation. These equations are already derived and provided by several researchers, and they are available in books. So, for orthokinetic processes, they can be written as log of dt by d naught is equals to a2 plus b2 t. This d naught is the initial size of the particle, dt is the enlarged size of the particle after time t. Okay. This a1, b1, a2, b2 are a kind of constants. So, these equations are valid for initial stages of agglomeration only. Otherwise, according to them, if you keep on increasing the time, then indefinitely increase the size of the particles. Okay. So, that we do not want. We want size enlargement, but controlled size enlargement, so that we can use them as a kind of workable units, so that we can transport those solids comfortably, and then subsequent process may also take place subsequently without any problem in flowability or conveying of those particles. Okay. So, that is the reason these equations are valid only for initial stages of agglomeration, otherwise they would indicate an indefinite increase of size dt with time t. Dt is agglomerate size at time t, dimensions of A1 is in meter cube, A2 is dimensionless, B1 is meter cube per second, and then B2 is second inverse. These kind of units these constants are having. Then finally, the characteristic time of a size enlargement process. There are different characteristic times are available, but we take two of them which are famously accepted. Von Smoluchowski has characterized the suspensions by a half time designated by t, which is defined as the time taken to half the number of original particles in a monodispersed system. You have a monodispersed system, let us say 1000 particles you have initially, right. So, now you are doing the agglomeration, so that the number of particles are joining together and then bigger particles are forming. So, obviously, number of particles will reduce, though the weight may be remaining same. So, when this 1000 number of particles reduced to the 500 number of particles by agglomeration process, how much time it has taken, that is known as the half time, and this time is taken as a kind of characteristic time by according to the researchers von Smoluchowski. There is another characteristic time definition. Walton, who defined an agglomerating system as one in which more than 10% of original number of particles has agglomerated in less than 1000 seconds. You take a system, very fine particles, let us say again you take 1000 number of very fine particles, right. So, if 10% of those particles, that is 100 particles, if they are agglomerating within 1000 seconds, then you can say that system is a kind of agglomerating system according to Walton. And these are a kind of few characteristic definitions, right. So, which may be important in designing of these processes, etc. Size enlargement processes, etc. they may be important in designing. Finally, stability of agglomerates. Stability of agglomerates may be increased by mechanical interlocking that may occur between particles in the form of long fibers. In order to increase the strength of the aggregate, often liquid binders are used to fill the pore spaces between the particles. When you, let us say, when you take 3-4 particles, 2 particles like this, another particle here, another particle here. So, between the particles, the interstitial spaces whatever are there, those interstitial spaces may be filled by some kind of liquid binders, so that the porous space between the particles that can be filled in, and that will, after drying, that will be providing a kind of enough strength for these aggregates. And then amount of binder is obviously function of the interstitial space of the particulate mass. Voidage are interstitial spaces that you can say. So, that how much binder, what is the amount of binder is required, obviously it will be a function of voidage of particulate mass or interstitial spaces of that particulate mass whatever we have taken. Voidage is further strongly influenced by the size distribution and shape of the particles, right. If the particle are very small finer sized particles, then voidage may be small. If you have a kind of a bigger particle or mixed particle kind of thing, then voidage may be large. So, accordingly the shape of the particles, if you have a spherical particles, then voidage may be different. If you have the cylindrical particles, then voidage may be different for a same packing height, etc. For the same weight of the material, same density, but the shape if you change, then voidage, the voidage that is going to be formed because of this fine agglomerates is going to be different. That is what I mean by voidage is further strongly influenced by size distribution and shape of particles. Wide size distributions generally lead to close packing requiring smaller amounts of binders. So, if you take the wider size distribution of the particles in general, then you need a less amount of binders for agglomeration, because the voidage space is less or interstitial space is less in the case of wide size distribution. So, that is the reason you may need only small amount of binder if you have a kind of wide size distribution particles. So, these are some details about the agglomeration, why we need the agglomeration, what are the agglomeration methods, how to do agglomeration by different types of forces, etc., and then typical agglomeration circuit, etc., that we have seen. We have also seen the agglomeration stability also we have seen. So, next lecture we will be discussing about the Equipment available for this size enlargement. The details presented in this lecture primarily are taken from this reference book, Perry's Chemical Engineer's Handbook by Green and Perry. Some information is also taken from Unit Operations of Particulate Solids, Theory and Practice, Ortega Rivas, and then Coulson and Richardson's Chemical Engineering, second volume by Richardson and Harker, and then a few details from the Unit Operations of Chemical Engineering by McCabe, Smith and Harriet. Other references that may be useful: Transport Processes and Unit Operations by John Coplis, and an Introduction to Chemical Engineering by Badger and Banchero. Thank you.